Today we talk about the Z transform. It is a tool for discrete time signals and systems. It works like the Fourier transform but gives us more power. We use it a lot in digital signal processing, control, and communication. In this chapter, we learn what the Z transform is, how it works, its key properties, and how to use it in real problems. Before we start this chapter, please note that our final exam is coming up. Okay, everyone, we are moving from the DTFT to the Z transform. The DTFT looks at frequency, but it only works for stable signals. That's a big limitation. The Z transform is much more general. It can handle both stable signals and unstable signals. First, let's look at the Z transform itself. It uses a complex variable called Z. Z equals R times e to the j omega. The definition is given by the equation. When the magnitude of Z equals 1, the Z transform becomes the DTFT. So the DTFT is limited because it only works for signals defined on the unit cycle when the magnitude of Z equals 1. The Z transform is more general. It uses the variable Z, and it includes both a magnitude R and an angle omega. This extra magnitude part let the Z transform work with unstable signals too. Then we will include the region of convergence, or ROC. The Z transform has an ROC. It is a shaded region in the Z plane. Look at this diagram. The ROC is the set of Z values where the transform works. It also provides key information about the signal's stability. Again, DTFT is a special case of the Z transform. When Z equals e to the j omega, the Z transform reduces to the DTFT. If the ROC includes the unit circle, like this, the Z transform can represent the DTFT. So what's the relationship between the figure of DTFT and the Z transform? This is a drawing made by one of your seniors. You can see DTFT is located on the unit circle of Z transform. We use the Z transform to study discrete time LTI systems. It is a tool that extends the Fourier transform. It helps us solve more general problems in signal processing. We first saw the Z transform in Chapter 3. In a discrete time LTI system, we write the input as this, Z to the n. Here Z is a complex number. Z equals R times e to the j omega. The output of the system is this. The input and the output have the same basic signal Z to the n. Here, h of Z is a function of Z. It shows how the system behaves in the Z domain. We call x of n equals Z to the n an eigenfunction the system gives a scaled version of the input. The scale value h of z is the eigenvalue. In Chapter 5, we saw the link to the Fourier transform. If z equals e to the j omega, then the z transform becomes the Fourier transform. So the Fourier transform is a special case of the z transform. The z transform is the general form. The complex variable is z equals r times j omega, and it has both magnitude r and an angle omega. Now we look at the relationship between the z transform and the DTFT. The DTFT changes a discrete time signal x of n into its frequency form x of e to the j omega. It uses e to the j omega. Here, omega is the frequency. The signal x of n in the time domain matches x of e to the j omega in the frequency domain. We have a formula like this. The inverse DTFT takes the spectrum back to the time signal. The z transform is a more general tool. It uses z equals r times e to the j omega. Here, r is the magnitude, and omega is the angle. So in the z domain, we show signals on the z plane. The z transform maps the signal into its z domain form. This plane includes the unit circle z equals e to the j omega. So the z transform becomes the DTFT on the unit circle. We can use this formula to show their relationship. For a general point, z equals r times e to the j omega. The z transform becomes this. This shows the z transform is the DTFT with an extra scaling term r to the minus n. So the DTFT is the z transform on the unit circle. If we use x of n times r to the minus n and take its Fourier transform, it becomes x of z. The z transform adds more flexibility because it uses both the magnitude r and the angle omega. In this example, we look at this signal again. Here, a is a constant, and the magnitude of a is smaller than 1. We want the Fourier transform and the z transform of the signal. The Fourier transform comes from the sum of x of n times e to the minus j omega n. This is example 5.1. We use the formula for the first term and the ratio of geometric series. So the result is this. The Fourier transform works only when the magnitude of a is less than 1. When a is between 0 and 1, the signal gets smaller with time. When a is between minus 1 and 0, the signal flips sign and also gets smaller. Now we find the z transform. We use the formula of x of z. The result is x of z equals z over z minus a. The absolute value of a times z to the minus 1 must be less than 1. So the z transform works only when the magnitude of z is larger than a. The ROC is the shaded region outside the circle with the radius a in the z-plane because the magnitude of z must be larger than a. So the key ideas are: the Fourier transform works only when the magnitude of a is less than 1. The z transform works only when the magnitude of z is larger than a. Let's summarize this example. It shows the z transform works for more signals than the Fourier transform. For the Fourier transform x of e to the j omega, it converges only when the magnitude of a is less than 1. For the z transform x of z, the convergence depends on the magnitude of z. It works when the magnitude of z is larger than a. Now let's look at the cases based on a magnitude. The z-plane helps us see where the z transform converges. When the magnitude of a is smaller than 1, the Fourier transform converges because the signal x of n gets smaller over time. But the z transform may not converge if the magnitude of z is smaller than the magnitude of a. So x of z is not valid for those z values. If the magnitude of a is larger than 1, the Fourier transform does not converge because the signal grows. But the z transform can still converge when the magnitude of z is greater than a. This shows that the z transform works for more signals because it can converge in a specific region in the z-plane. In this example, we look at the z transform of a left-sided signal. The term u of minus n minus 1 means the signal exists only for negative n. For n smaller than 0, the signal grows when the magnitude of a is smaller than 1. Or it gets smaller when the magnitude of a is larger than 1. For positive n, the signal is 0. We use the formula for the z transform. We change the interval of summation. We use the formula for the first term and the ratio of a geometric series. So the result is this. X of z equals z over z minus a. This result is the same as example 10.1, but the absolute value of a to the minus 1 times z must be less than 1 to make it stable. So the z transform works only when the magnitude of z is less than a. The ROC is the shaded region inside the circle with radius a. This means the transform works only when the magnitude of z is smaller than a. Now let's compare this signal with the signal in example 10.1. For this right-sided signal, the ROC is the magnitude of z larger than radius a. That is the region outside the circle. For this left-sided signal, the ROC is the magnitude of z smaller than radius a. This is the region inside the circle. This example shows how the z transform works for signals defined for negative n, and how the ROC tells us where the transform is valid. Next, we find the z transform of this signal. This signal has two parts. They are two right-sided signals. This example shows how to write the z transform as a rational function, and how to find the poles and zeros. These poles and zeros tell us how the system behaves. From the standard formula for a to the n times u of n, this term has the z transform of this, valid when the magnitude of z is larger than 1/3. Z equals 1/3 is a pole, so we place an X on the z-plane to show it. Please remember to draw it this way when I ask you to show the ROC on a z-plane. We sketch the real axis and the imaginary axis, and we add a solid circle to show the unit circle, and then we put zeros and poles on it. This term has the z transform of this. It's valid when the magnitude of z is larger than 1/2. So z equals 1/2 is a pole. We place an X on the z-plane to show it. So the z transform of the full signal is a subtraction of this too. The ROC is the magnitude of z larger than 1/2. We can write the z transform as a rational function. Here n of z, the numerator, gives the zeros of x of z. D of z, the denominator, gives the poles of x of z. So in this example, the poles are at z equals 1/3 and z equals 1/2. The ROC is the magnitude of z larger than 1/2. This is the shaded region outside the circle in the z-plane. So the poles mark where x of z goes to infinity, and zeros mark where x of z becomes 0. The ROC shows the region where the z transform converges. If z is on the unit circle, we get the Fourier transform. In this example, the Fourier transform exists because the region of convergence includes the unit circle. The unit circle lies inside the valid region. So DTFT is well defined for this signal. In this example, we find the z transform of a signal made of an exponential decay and a sinusoidal term. This example shows how we break the signal into simple parts. Find each z transform, and then look at the poles and zeros. Using the sinusoid to exponential idea, we can rewrite the signal. This breaks the signal into two terms. They are two right-sided signals. The z transform of this follows the standard form in the first example of this chapter. For this term, the z transform uses the same rule, and the ROC is the magnitude of z larger than 1/3. For this term, the z transform also follows the same rule. The ROC is again the magnitude of z larger than 1/3. The z transform of the whole signal is the difference of those two terms. We can simplify it into a rational form with poles and zeros. The poles and zeros show how the system behaves. There are two poles. They sit at these two locations. Their magnitudes are 1/3. And the zero sits at the origin. The ROC is the magnitude of z larger than 1/3. The shaded region lies outside the circle in the z-plane. So this example shows how we break a sinusoidal signal into exponential parts, how we write the z transform as a rational function, and how the ROC sits outside the circle with radius 1/3. And please remember to put an X mark of the poles, a circle to represent the zeros, and the ROC lies outside of the pole. The z transform extends the Fourier transform by using a complex variable z equals r times e to the j omega. It lets us study a wider set of signals, including signals that grow or decay. To understand the z transform, we also need to understand the region of convergence, or ROC. The ROC tells us where the z transform is valid. It helps us see if a signal grows, decays, or oscillates. Next, we look at how the ROC affects the way we analyze signals. We look at the region of convergence, or ROC, for the z transform. The ROC is important because it tells us where x of z is valid. It also helps us see if a signal grows, decays, or oscillates over time. So the first property, the ROC forms a ring in the z-plane. The ROC is a ring centered at the origin. The convergence depends only on how far z is from the origin, not on the angle. So this means the ROC can be inside a circle, outside a circle, or between two circles. The shaded areas shows different possible ROCs. The second property, the ROC cannot contain any poles. Poles are points where x of z becomes infinite. So the ROC never includes a pole. If a system has poles at 1/3 and 1/2, the ROC can be in 3 places: outside both poles, inside the smaller pole, or between the poles. So the ROC forms a ring in the z-plane. It depends on the radius r, and it cannot include poles. Let's continue with the ROC for the z transform. Now we look at signals that have finite duration and see how their ROC behaves. Property 3. ROC for finite duration signals. For this type of signal, the values of x of n are non-zero only between 2 points, n1 and n2. So the signal exists only in that short range. The ROC is the entire z-plane because the signal has only a finite number of non-zero samples. But there may be 3 special cases. If the signal is non-zero only for non-negative n, this means n1 is greater than or equal to 0, then the ROC does not include z equals 0 because the transform blows up at the origin like this. If the signal is non-zero only for negative n, then the ROC does not include z equals infinity. This means n2 is smaller than or equal to 0. So the transform blows up far away from the origin, like this. If the signal spans both negative and positive n, then both z equals 0 and z equals infinity are excluded from the ROC. So let's look at the unit impulse as an example. For delta of n, the z transform is just a constant. So the ROC is the entire z-plane, including z equals 0 and infinity. For delta of n minus 1, the z transform shifts by 1 step. So it's the case when n1 is positive. Here you can see the ROC is the whole z-plane except z equals 0 because there is a pole at the origin. And for delta of n plus 1, this is the third case when n2 is smaller than 0. The ROC is the whole z-plane except z equals infinity because the transform blows up there. So we can summarize. If a signal has finite duration, the ROC is the entire z-plane except possibly z equals 0 or infinity. For a signal like delta of n minus 1, and delta of n plus 1, the ROC may include or exclude these points depending on where the non-zero samples occur. Next, we look at the ROC for a right-sided signal in the Z-transform. A right-sided signal means x of n is 0 for all n smaller than n1. So the signal starts at n1 and continues toward positive n. The ROC rule says if a circle with radius r0 is inside the ROC, then every value of z with a radius larger than r0 is also inside the ROC. This means the ROC is tends outward from that circle. The idea is simple. If the signal converges on the circle with radius r0, then it will also converge for any value larger than that. The reason is that the term depends on the radius becomes smaller when the radius grows. So the ROC expands outward. One more point, if n1 is negative, then z equals infinity is not in the ROC. If n1 is larger or equals 0, then z equals infinity is in the ROC. This matches what we said on the previous page. Now we look at the ROC for left-sided signals and two-sided signals in the Z-transform. A left-sided signal means x of n is 0 for all n greater than n2. So the signal stops at n2 and extends toward negative n. The ROC rule says if a circle with radius r0 is inside the ROC, then everything inside that circle is also in the ROC. This means the ROC moves inward toward the origin. If the signal converges at radius r0, then it will also converge for any smaller radius. The ROC extends inward. One more point, if n2 is positive, then z equals 0 is not in the ROC. If n2 is smaller than or equals 0, then z equals 0 is in the ROC. We learned this earlier in property 3. So for left-sided signals, the ROC moves inward from the largest radius where convergence happens. Now, let's look at two-sided signals. For two-sided signals, the ROC is a ring in the z-plane. If a circle with radius r0 is inside the ROC, then the ROC lies between two radii, one smaller and one larger. So the ROC forms a ring around the origin. In this example, we find the Z-transform of a two-sided signal. The signal is this. We can split it into two parts, a right-sided part and a left-sided part. Here, B is a positive number. Because the signal has both sides, the ROC depends on both parts. For the right-sided signal, the Z-transform has an ROC outside a circle with radius B. So the ROC is the magnitude of Z greater than B. For the left-sided part, the Z transform has an ROC inside a circle with radius 1 over B. So the ROC is the magnitude of Z smaller than 1 over B. Now we check whether the two ROCs overlap. If B is larger than 1, the two ROC does not overlap. There is no region that satisfies both conditions. So the Z transform does not converge. If B is smaller than 1, the two ROCs overlap between radius B and radius 1 over B. So the Z transform converges in that ring. The ROC is the region between the two circles. So when B is smaller than 1, the Z transform converges, and the ROC forms a ring in the Z-plane. Next, we talk about how the ROC for the Z transform changes based on the type of signals and the poles in the Z-plane. Property 7. If x of Z comes from a rational function, meaning it's a ratio of two polynomials, then the ROC is determined by the positions of the poles. The poles marked where the transform becomes infinite, so the ROC must avoid those points. Property 8. For a right-sided signal, the ROC is outside the pole with the largest radius. If the system is causal, the ROC can also include Z equals infinity. This matches what we said on page 13. Property 9. For a left-sided signal, the ROC is inside the pole with the smallest radius. If the system is anti-causal, the ROC can include Z equals 0. This matches what we said on page 14. If the signal is two-sided, the ROC lies between two poles and forms a ring in the Z-plane. Now we look at example 10.8. We have a Z transform with poles at 1/3 and 2, and the two zeros located at 0. These points appear on the Z-plane. If the signal is right-sided, the ROC is outside the outer pole. So the ROC is the region where the magnitude of Z is greater than 2. In the figure, the shaded area covers the outside of the circle through the pole at 2. If the signal is left-sided, the ROC is inside the inner pole. So the ROC is the region where the magnitude of Z is less than 1/3. The shaded area covers the inside of the circle through the pole at 1/3. If the signal is two-sided, the ROC lies between the two poles. The shaded region forms a ring between the circles at 1/3 and at 2. We have learned about the ROC for the Z transform. Now we move on to the inverse Z transform. The inverse process takes a function in the Z domain and brings it back to the time domain. We use the idea from the DTFT to help us recover the original signal. The DTFT formula gives us a way to move from a frequency domain expression back to a time signal. We follow the same idea here, but we work on a contour in the Z-plane instead of the unit circle. So the inverse Z transform lets us rebuild the time signal from its Z domain form. In the next slide, we look at several methods we can use. In this slide, we introduce the inverse Z transform. The inverse Z transform lets us recover the time domain signal x of n from its Z domain form x of z. To do this, we integrate x of z along a circular path in the Z-plane. First, we write the Z transform using the form z equals r times e to the j omega. Here, r is the magnitude, and e to the j omega is the complex exponential. When we plug this into the Z transform, we get a sum that connects the Z domain with the frequency domain. To compute the inverse Z transform, we use the idea from the inverse DTFT. The formula for x of n from chapter 5 appears in the gray box on the right. In this formula, x of r times e to the j omega is the Z transform evaluated on the circle with the magnitude of z equals r. Now we change variables. We let z equals r times e to the j omega, and the small change in z becomes dz equals jz d omega. When we replace this into the formula, we get the contour integral form of the inverse Z transform. This form says to find x of n, we integrate x of z times z to the n minus 1 around a circle in the ROC. The integration is taken counterclockwise along the circle with the magnitude of z equals r. The orange arrows in the figure shows this direction. The variable omega represents the angle as we move around the counter. Next, we learn how to find the inverse Z transform using partial fraction expansion. This method helps us break the Z transform into small and simple pieces that are easy to invert. We start with a Z transform that can be written as the sum of simple terms. Each term has a constant and a pole. So each piece corresponds to one pole at some value ai, and the constant tells us the weight of that pole. Now, the ROC tells us what kind of time signal we get from each term. Case 1. ROC is outside the pole, like this, outside the circle that passes through the pole. In this case, the inverse Z transform gives a right-sided signal. Its form is a constant times ai to the n multiplied by the step function u of n. The step function keeps the signal from non-negative time. Case 2. ROC is inside the pole. The shaded region is inside the circle through the pole. Here, the inverse Z transform gives a left-sided signal. Its form is a constant times ai to the n multiplied by u of minus n minus 1. The step function keeps the signal for negative time. So the term big AI and small ai come from the partial fraction expansion. The step functions show whether the signal lives on the positive side or the negative side of time. The ROC tells us if each piece is right-sided or left-sided based on the location of the shaded region relative to the pole. Next, we find the inverse Z transform of a given function using partial fraction decomposition. The inverse Z transform let us move from x of z back to the time signal x of n. We start with the given Z transform. We rewrite it as the sum of two simple terms using partial fractions. One term with a pole at 1/4 and one term with a pole at 1/3. Each term matches a known inverse Z transform. For the first term, the inverse is a right-sided signal that looks like 1/4 to the n times the step function. Its ROC is outside the circle with radius 1/4. For the second term, the inverse is 2 times 1/3 to the n times the step function. Its ROC is outside the circle with radius 1/3. Now we combine the term and look at the ROC. The figure on the right shows three possible ROCs on the Z-plane. Case 1. The ROC is outside the larger pole. If the magnitude of Z is greater than 1/3, the signal is right-sided. The solution is the sum of the two right-sided terms. Case 2. The ROC is between the poles. If the magnitude of Z is between 1/4 and 1/3, the signal is two-sided. The first term stays right-sided, and the second term becomes left-sided. It forms a ring. Case 3. The ROC is inside the smaller pole. if the magnitude of z is less than 1/4, both terms become left-sided. So the ROC depends on the poles. The ROC also tells us whether the result is right-sided, left-sided, or two-sided.